Hi fellows, today we resume our lectures on geometric algebra, and let's review some of the terminologies and items regarding geometric algebra of vector space, geometric algebra of vector space V of PQ, we write this way, where we have this is G for geometric algebra PQ is the signature. This is geometric algebra of the vector space, place and time. So PQ in itself is called the signature. PQ is the signature of the vector space. This is PQ. P we have refers to the number of unit vectors, EIs, that's equal to plus 1, which means EI square equal to 1. Means E1 square, which is E1, which is equal to 1. Or E1 is exactly the same as E1 dot E1, as we said, because E1 wedge E1 is 0. So E1 square is 1, or E2 square, for example, is equal E2 which equals to 1, E3 square, E3 which equals to 1. This is usually the case for Euclidean three-dimensional space, E1, E2, E3, and we don't have any Q, 0 Qs. In other spaces, like relativity space-time, we have the P. It's also conventional. Some of them use P equal 1, the signature 1, 3, PQ. This is 1, 3, meaning P equal 1, which means E0 square equal plus 1 is the plus. E0, which is the unit vector for time, and for space, all negative. E1 square is minus 1, E2 square is minus 1, E3 square equals minus 1. This is just terminology and conventions. Let's move on. Today hopefully we take a new subject, an easy one, but very important, which leads to more important one. Today we take only this one, reflections. The reflection of the vector space. Reflection of the vector in the vector space. Suppose we have a vector A. This is our reference vector A. I will not use arrows for simplicity. A, B, C small letters will refer to vectors, and capital letters multi-vectors. B for bivector, T for trivector, and so on. Alphas, beta, Greek letters for will be saved for scalar functions. So this is our reference vector. Our reference vector. We take this vector, should be straight, vector V, which we decompose to V parallel and V perpendicular. What do we mean? V parallel is V parallel to this vector A. V parallel equals V parallel to A. And this one, V perpendicular equals V perpendicular to A. If we go the other way around, if we go up, same magnitude, opposite direction, what is it? V perpendicular and the negative. So what will this compose? This will, when I get the resultant of V parallel and minus V perpendicular, what do I get? Let's see. We get this vector, we call it VR. Now, we want to find an expression for VR. This is our task. VR, what is VR? And we will see how to find R. We will go through a process and through derivation, which will give us some techniques in handling these vectors in geometric product. Let's see. Now, we said that V equals V parallel to A and V perpendicular to A. This is the decomposition of V along or parallel to vector A and perpendicular to vector A. As we said, let's keep a reminder here. This is A, that was our V, and this is V parallel, and this is V perpendicular, and minus V perpendicular, this is the other way around. And V parallel shares with V and V reflected. So we only need to find the other one and find the expression altogether. What is AV? A times V equals A. What is V? We write V in its components along and perpendicular to A. So AV is AV parallel plus AV perpendicular. AV perpendicular. Now, let's see. Let's take them one by one. Let's call this, let's give them numbers. V. Let's give this one number 1. Let's give it different color. This is number 1, V, and we give number 2 to AV. This one, number 2. Now, this is, we said AV. Let's take AV parallel. We look at AV parallel. This is geometric product, which is, as we said, is the sum of dot product A dot V, A wedge V parallel. Two parallel lines or vectors, two parallel vectors, their wedge product is 0. So this goes to 0. So AV geometric product is the same as A dot V, the dot product. The dot product commutes, which is the same as V parallel dot A. V parallel dot A, let's call this 2 prime, for example. 2 prime. Now, VA is the other way around. Look, AV is, so now VA is what? VA is V dot A plus V wedge A. Now, let us decompose this to V parallel, V perpendicular. A is equal to V parallel and V perpendicular to A. V parallel and V perpendicular. This is equal to, let's take V parallel A. We took A V parallel. Now we want to find the opposite. V parallel A, this is geometric product. V parallel dotted with A and V parallel wedge A. Again, this is 0 because they are parallel. So V parallel A is equal to V parallel dot A, and this also equals to A dot V parallel, because these two, we know the dot product commutes. So the geometric product V parallel is V parallel A. Look at V parallel A here. And AV parallel. Both of them A dot V, this is A dot V parallel, and V dot A, because these two commute, and V dot A. So therefore AV parallel equal to V parallel A. This is important. The geometric product of the parallel component of the vector V, the parallel component to A, the geometric product with A is commuting. So AV parallel equal V parallel A. This is important fact. Now let's go to the other one. Keep in mind this one. Now let us take AV perpendicular geometric product. A dot V perpendicular plus A wedge V perpendicular. A dot V perpendicular is perpendicular to A, so this one is 0 this time. So we have AV perpendicular equals to A wedge V perpendicular, but A wedge V the wedge product between vectors, not always, between vectors commutes. It commutes. Why? Because of the orientation. One is oriented in one way, the other one is in the other way. If you remember, this is it. One goes this way, the other one goes the other way, so there is a negative. So these two commute. It is minus VA. Now let's take V perpendicular A. This is geometric product. This is geometric. So you see the geometric product AV perpendicular is the same as the wedge product in one way, in the same order, AV, A wedge V perpendicular. But when I switch the other way around, you get a minus sign. Let's see what happens here. It should be clear for you now that this is V perpendicular dotted with A plus V perpendicular wedge with A. The dot product of A with the vector perpendicular to it is 0. So again, V perpendicular A is equal to V perpendicular wedge A, which is minus A. Minus A, we said it commutes, minus A wedge V perpendicular. This is another very important fact. So we have these two. Let us see. What do we have? We have these two. V perpendicular A, A, V. Look, AV perpendicular is minus VA. Here it is VA. So one is the negative to the other. This is the same order. The order is important. V wedge A, V perpendicular wedge A. This is a positive. This is negative. So A V perpendicular is the negative with V perpendicular A as geometric product. So we have two things now. We have these two commute, the geometric product of A with the component of vector parallel to it, it commutes as geometric product. A V parallel equal V parallel A. While the geometric product of A V perpendicular is the negative anti-commute. So let us see what we can arrive at from here. Let's summarize what we got. Now we have AV, the geometric product, as AV parallel plus AV perpendicular. We have it. Where did we have it? The geometric product. We said AV is AV parallel, equation 2, plus AV perpendicular. We just copy it. This is it. We copied this. Together with, we said AV parallel equal V parallel A, commuting, and AV perpendicular is minus V perpendicular A, anti-commuting. So what do we get? We get AV equals, instead of A V parallel, this commutes, I want V parallel. I want to keep A on the right hand side. A, V parallel A plus AV perpendicular. Also I want to switch over minus, so here anti-commute. This one anti-commutes. I get minus VA. So AV equals V parallel minus V perpendicular acting on A. I took A out. Pardon me. So now let us multiply to the right. Right multiply. R-I-G-H-T. Right mult by A. So we have A VA equal V minus V perpendicular times A times A. Now let's go back to our drawing. What did we have? We have, this is the A, this is the V, this is V parallel, this is V perpendicular, and this is minus V perpendicular. And this V parallel, look, V parallel minus V perpendicular. This is V reflected, which is what? This is V parallel, which is, this is V reflected, AA, sandwiched, AVA. So the reflected times AA, AA is A square. So VR, A square, this is our reference vector A. This is the angle theta. This is theta. A, V, A. Now, when A is unit vector, A يساوي 1 magnitude. Then A square is 1. And I get VR, the reflected is simply AVA. Is what? AVA, where A is what? A unit vector. A unit some vector around which the reflection takes place. Between V through A is reflected to VR. So the reflection is AVA. AVA. That's it. Thank you very much. Thank you very much.